In this problem, we're adding a strong base to each of 4 different solutions and asked to consider the implications for the pH. Parts A and C of this problem will be very similar to each other, and parts B and D will be very similar to each other. In part A, notice that we're adding a strong base to a solution that has a weak base already present in it. Of the two substances, the strong and the weak base, the one that will far predominate in importance when determining pH is the strong base. The K value for a strong base is infinity, and the K value for the weak base they give us as 1.1 times 10 to the negative 8. So to find pH, we really need to just consider the strong base. In this case, we'll find the pOH by taking negative log of hydroxide concentration, and that can be found by just considering how many moles of the strong base were added and the volume of 1 liter. We simply divide 0.02 by 1. And you might say, why are we ignoring the weak base? Doesn't it also contribute hydroxide ions? Yes, it does, but not nearly as much. It would contribute a tiny, tiny fraction, a fraction so small that it's not important. To find pH from pOH, we just subtract 114, and we arrive at 12.46. Let's jump to part C as well. We'll do this A and C together. In part C, we have pure water and we're adding a strong base. The calculations for part C are exactly the same as what we found in part A. Whereas in part A we got to ignore the effect of the weak base. In part C, water is also a weak base. It's just very, very weak. Its K value is 1 times 10 to the negative 14th. So the calculation is exactly the same, and we arrive at the same pH as we did in part A, 12.46. Now on to the more interesting parts of this problem, parts B and D. Let's see here. Okay. In part B, we're adding a strong base to a solution that has an acidic salt in it. And the reason I know it's an acidic salt is because the positive ion is the conjugate of a weak species. So for part B, let's first draw the reaction vessel and everything that is in it. So they told us we're adding sodium hydroxide. I'll write that as broken apart because all salts are strong electrolytes. And we also have the acidic salt, HONH3, paired with chloride ion. I'll write that as broken apart. And as with any aqueous solution, water is present. We have a strong species here. It's a strong base species. It wants to react with the best acid available to it. So acids react with bases always. In this case, well, it's going to avoid the other negative ion. The metal ion doesn't have any bearing on this problem because it's not highly charged enough to have any acidic properties. So we're left to consider which acid is better between water and HONH3. Water's K value is 10 to the negative 14th. The K value for HONH3, they didn't give it to us, but we can eyeball it. If we know that water's K value is 10 to the negative 14th, and the KB of HONH2, they gave us up above is 1.1 times 10 to the negative 8th. If I divide KW by KB, I should get KA. And we would get something on the order of 10 to the negative 6th, which means that your best acid is HONH3. Students, it will almost always work out that the substance that is the best acid or base is not water. Once we know the best acid to react with our strong base, we're going to write a reaction to completion table. which is unlike an ice table in that we're going to keep track of not initial changes in equilibrium, but rather before and after lines of the table. And we'll also work it out in units of moles rather than molarity. In order to predict the products of this equation, I'm thinking of the definition of a base, the Bronsted-Lowry definition, and the definition of an acid. Bases by definition accept protons, and acids by definition give off protons. So after the acid gets rid of a proton, we're left with HO and H2, one less H. And after the hydroxide picks up a proton, it becomes water, H2O. We'll write our before and after tables. Water, since it's a pure liquid, drops out of consideration, just like we did with ice tables. If we read the problem carefully, they'll give us numbers of moles. Up at the top, they said we had 0.02 moles of sodium hydroxide. So that means that initially we have 0.02 moles of hydroxide. And in part B of the problem, they tell us we have a solution of 0.18 molar HONH3Cl in a 1 liter container. So that same number, 0.18, is going to be the number of moles. And then we don't initially have any HONH2. Of the two reactants, one of them will go all the way down to 0. That's going to be the one with the smaller number of moles. Hydroxide in this case. It goes down by 0.02. The other reactant will go down by that same amount, but it's not going to end up with 0 for its final number of moles. On the product side of the equation, we'll go up by that same amount, 0.02, to give us a final number of moles of 0.02. Now we've accounted for the reaction to completion, and we've got our conjugate acid of a weak base, still with some number of moles at the end of the reaction to completion, and the weak base. If you have at least some acid and some base at the end of the reaction to completion, we can find the pH of the solution using the Henderson-Hasselbalch equation. Even though they didn't give us a Ka value directly, we'll find it indirectly. The Ka will always be Kw over the given Kb value. In the problem, they told us the Kb is 1.1 times 10 to the negative 8th. And then we'll plug in our number of moles of base and acid. And you don't need to be concerned that the Henderson-Hasselbalch equation calls for molarity and we're plugging in numbers of moles. In this particular example, the volume of the reaction vessel is 1 liter, so the number of moles is also the molarity. But even if that weren't the case, the ratio of moles is the same as the ratio of the molarity of the reaction of the base and the acid because they're in the same reaction vessel. So crunching a few numbers here, we arrive at 6.041 and negative 0.903. And if we add those together, we get 5.138 for part B. Part D is going to look almost exactly the same, except we'll have a weak base present. And note that in this reaction to completion table, the number of moles of the weak base was initially 0. In part D, that it's going to be something other than 0. Let's start by drawing that reaction vessel. Sodium hydroxide, since it's a strong electrolyte, will exist broken apart in solution. The weak base is there. The acidic salt is also there, and that's broken apart into its ions because all salts are strong electrolytes. In this reaction vessel, we have a strong base species that wants to react with the best acid available to it. Well, let's cross out some things that it wouldn't react with. Right off the bat, we could say, hey, a negative hydroxide ion is not going to react with a negative chloride ion. Opposite charges attract and similar charges repel. A strong base won't react with a weak base. Bases are trying to do the same thing. And the metal ion isn't of a high enough charge to have any bearing on pH. That leaves us with water and the conjugate acid of a weak base. Water is almost never going to be the substance with which a strong species reacts because its K value is so small, 10 to the negative 14th. HONH3, if we were to find a Ka value for it, we would take Kw divided by the Kb of its conjugate, 1.1 times 10 to the negative 8th, and you get something on the order of 10 to the negative 6th. That's a much bigger number, 10 to the negative 6th, than the K value for water, which is 10 to the negative 14th. So when writing a reaction to completion, we'll include hydroxide ion and the conjugate acid of the weak base. To predict the products, think of the definition of an acid and a base. Acids want to give off protons and bases want to accept them. So HONH3 is going to become HONH2 after giving off a proton, and OH minus becomes H2O. We'll set this up as a before and after table, and we'll keep track of the substance's numbers of moles, not the molarity. Water drops out of consideration since it's a pure liquid. Next, we read carefully what the problem gives us in terms of information about the substances being mixed together. At the very top, it says that we've added 0.02 moles of sodium hydroxide, which means that when that salt breaks apart, you have 0.02 moles of hydroxide. And in part D, we have a mixture of 0.18 molar weak base and 0.18 molar acidic salt that contains HONH3. They're both in a 1 liter reaction vessel. So if you take the volume times the molarity, 0.18 is the number of moles. Of the two reactants in this equation, one of them is going to go all the way down to 0, and that's the one with the lower number of moles. Hydrogen goes all the way down to 0 because it has a lower number of moles than HONH3. But the HONH3 goes down by the same amount. It just brings its total down to 0.16. On the other side of the equation, the number of moles goes up by 0.02, not down. And at the end of this reaction to completion, we have the conjugate acid of a weak base and a weak base. So long as there's at least some of an acid and a base species left after the reaction to completion, we can use the handy Henderson-Hasselbalch equation. We don't have a Ka value directly. Instead, we're going to find it from Kw and the Kb of the conjugate. They gave us that the Kb of HONH2 is 1.1 times 10 to the 8th. We'll find that from Kw. And then we'll plug in the number of moles of base over the number of moles of acid. Keep in mind, the molar ratio is the same as the molarity ratio if it's in the same reaction vessel. And then it's a matter of number crunching. 6.041 plus 0.097, and that works out to be 6.138. That's our final answer.